Okay, there we go, hopefully. Okay, so I'm here to show you how to set up the build environment and yeah, get a running version of BART and then show some debugging examples. And I'm doing this in a virtual machine using a Debian that I prepared. So we can pretend this is just installed, but I actually pre-downloaded some packages, didn't install them, just to make this presentation go faster. And but yeah, this should work just as well on a live system. As I think we also explained yesterday, we're currently, I think, yeah, just because we develop on Debian, that is the system that is best supported, but we will change that in the future and also support a number of other Linux distributions. Okay, so let's get started. So if you want to actually develop BART, you will probably go to this website, this GitHub page again. And if you scroll down, you will find in download, you will find the source code. And you can actually just go to the GitHub repository, which is this. Oh, God. No one can read it. Way too big. Yeah, like this. And there's just a nice thing, clone or download. We can copy this link, go to a terminal anywhere, and just clone it. Which is not what's going to happen, because we actually first need Git. So if you don't have it installed on Debian, you can just do sudo apt install git. Actually, is this font big enough that you can read it well over the?
Yes.
Okay. Okay, finally we have Git. Now we can clone it. This should hopefully be very fast, depending on your internet connection, and you will have a new directory called BART. And if you go in here, you have you have the entire repository just as it is on GitHub. If you want to know how to build it, there are instructions, for example, in the README, not in the readme.md, which is just to look nice for GitHub, but in the README, which contains all of the gory details. And if you just go down, you can go. You find installation and prerequisites. So it needs some libraries. Yep, you can read it on your own. If you're using Debian, it actually just gives you the command that you need. We need GCC, the GNU C compiler collection. To have a C compiler, we use makefile, so we need make. We need the fastest Fourier transform in the West, FFTW, LAPACK for linear algebra, PNG, OpenBLAS, and also a Fortran compiler. But actually, with this command string, it should just work in Debian.
So while that's compiling, I just want to mention that there are also similar install instructions for other operating systems, although they may require a little bit more manipulation.
Yep, there's also instructions for Red Hat and CentOS, but I think we yesterday learned about some problems with Fedora, which should translate to problems on Red Hat and CentOS. And also instructions for macOS on Windows, but I've personally not tried those. Okay, so now we have all of the packages that we need. So we could just type make. And if we do, we actually do get a working BART version at the end. This will just take a while because BART actually contains quite a number of source code, quite a number of files. It's compiling all of those files one after the other. And yeah, actually, I don't actually want to run it to completion. It takes too long already. I don't want to wait that long. What we can do parallel builds with make. So we actually just completely saturate our CPUs and just compile everything as quickly as possible. For that, we have some variables. If we, for example, look at the make file, it will tell us about some of these variables that we can define. And one of them, that's somewhere in here. Oh, it's actually not defined. No, it's just parallel. So if you give it parallel equals 1, it will do a parallel build. At this point, let me just mention there are also lots of other things, like if you use the Intel MKL, the Math kernel library. We also support that with a flag. We have CUDA, which unfortunately I can't show because I'm using a virtual machine and I didn't figure out how to actually pass through my GPU here. And some other configurations here. So we could, in principle, just do make parallel equals 1 like this, just typing it on the command line and having it behind the make command. But that gets tedious if you want to do it for all of them. Like if we also want to do CUDA, we would do CUDA equals 1 and everything like that. And we would always need to remember to use the right options so that we get a working version of BART. So in BART, we actually implemented the way of making these changes permanent. We have a subdirectory, which is called makefiles. And in that, we can, for example, create a makefile.local. And in that, we can specify all of these options. For example, we want parallel equals 1. I want a debug build already for later. And I just save it. You can use any editor here. I just use VI because I'm comfortable with it. But I don't know, maybe I should have used nano. And if I now type make, probably take just as long because it's a virtual machine. But in principle, this is now doing a parallel build and also building a debug version. Or actually building the same BART executable with debug symbols in them.
Christian, there are some questions about the alternative way with make is make-j number of CPUs. Can you comment on that?
Yes. We are kind of using that internally. So if you actually go, if I now go to, auto completion is different. If we actually look at the make file and we are looking for parallel, we see we actually use make flags -j, which means not number of CPUs, but actually just do everything in parallel at once and let the operating system care about scheduling all of those processes. Just typing make -j4 on the BART on the command line here would not do a parallel build because we actually use a two-stage makefile. So our makefile calls itself after doing some pre-processing. So actual options to make are ignored. So you actually, for BART, you actually have to use the make parallel equals 1. But it seems like it's finished. So if I just look at this, I see, oh, there is a new file called BART. And if I run it, I see, okay, this is actually a version of BART. Now I could just go through all of these things and find out if it actually is a working version of BART, but that also seems very tedious. So we have tests for that. We have unit tests, which you can run just by running make utest for unit test. This will compile the unit tests and afterwards run them. And hopefully we get the good output. Yes, we get the nice output, all CPU unit tests passed. There are also some GPU unit tests, which again, I can't show because I can't compile it with GPU support. And this might take some time. There is also a make test. And this would now also run all tests in parallel. I'm not sure if I actually have enough RAM on my virtual machine, so I will run it not in parallel and just do make test parallel equals 0 to override it. And this will now just go through quite a number of tests while they are running, because I don't think that output is useful to a lot of people. We can actually look at how that works. So there are now a lot of new files here, but there's still a subdirectory called tests. So let's go there and look at it. This contains a lot of make files, which then actually, these make files then implement the tests. So let's look, for example, at what might be interesting, the FFT test. It's written in a bit of difficult way, but what it's doing in the end is running tests that, just some sanity tests for our FFT that actually does what we think it should be doing. or the same thing with pigs. This will run pigs reconstructions on like known data that we actually all create, that's not included in the repository, but that we create with BART, and we can see, we check if the outcome is as we expected.
Christian, so quick question. Can you just comment
sorry.
on the Can you comment on the difference between test and U-test and when those are used?
Oh, yeah, the tests are actually tests of the that use the BART tools. So they're like BART nlength will be in a test, and the unit tests are smaller tests for individual functions that you can't call with a command. So they are more internal tests.
Okay, and there's another question about GPU support. Do you require a certain version of CUDA?
To be honest, I'm not sure. We might require a minimum version, but it's probably quite low. So far, I think we have upgraded from all the way from CUDA 5 to CUDA 10, and we didn't have any problems. So yes, as we haven't found a non-working version of CUDA, we don't have any like documentation on which version we require, and I think for now we would just assume that most of them that people would install will work. Yeah, this is a bit unfortunate. I actually can't see the questions myself. Okay.
Yes, it should work with rather old versions of CUDA, so there's no strong requirement to have a new CUDA version.
Yeah. As you can see, the BART test is actually, the BART tests are still running. We try to include tests for all of the tools that we have, and for most of the different like reconstructions that make sense. Obviously, with something like pigs, which has in principle an unbounded number of regularization terms that you can all combine, it's not feasible to write tests for all of them, for all combinations, but we do try to test as much as we can. And in this case, actually, it seems to work. We have a, the tests are finished and none of them failed.
Christian, another question. Can you comment on what would happen if a test did fail? What we would see?
It would abort and then would show us which test failed. Let me check if I can actually make a test fail live. Could probably just ask one of these tests to not allow any deviation. And if I then only run that specific test, what? Oh, I changed something, yes. It would look like this. Yeah, so now we have make tells us tests, test end length, did not succeed. We have an error here. Yeah, and the error is that our normalized root mean square error is bigger than 0, which is always to be expected when doing something with floating point. But yeah, this is what a failing test would look like. Okay, so to actually to use BART, we talked about this viewer before. Oh, we have this viewer which we often use with BART. It's not the only way to look at BART files. I will also go ahead and build that. So for that, we can just go back to this GitHub page for BART, and if we go to examples, it says an image viewer for Linux and Mac OS can be found here. So this is also a link to a GitHub repository, and we can just also clone it.
You know that you can click on this symbol right to the link to get a copy?
Yes, I know, but I'm old-fashioned. So this then creates the view subdirectory, and if I remember correctly, I need some package for that. Yes, it also tells me I need libgtk3. Oh wow, that's a lot of packages. And this viewer is actually integrated with BART, so it uses a number of BART functions to actually work. So yeah, I will. Yeah, it requires some BART commit to actually work. Yeah, but I think that's at this point quite old. So to build it, it needs to know where BART is located, and for that we use the environment variable toolbox path. Using bash, we can just use source and then source from profile.h in the BART directory in BART scripts profile.h. Wait, what? I'm confused as to what happened there. Source BART scripts. Huh. Interesting.
Is it
That
the
for
error
some
from before?
reason closes. Yeah, but it closes my tab in this. I have no idea why. Oh wait, this is probably not bash, right? Is this bash? Is that the problem?
But why do you try profile?
Is that not the? Oh, it's not the right one.
It's not the right
What
one,
is?
yeah.
Oh, startup. Yes, I'm sorry. It's at the main directory. It's startup.sh. Yes, and now we have an environment variable toolbox path, which
But
just points to this.
Interesting effect.
Yes, interesting effect. It is not what I wanted to happen. That's what you get for trying to do things live. And the viewer, it should be easy to make just by using make. And yeah, it created a viewer. So let's try it actually. No. By just, for example, creating a phantom and then looking at it. Oh, I have the same problem that the other person also had. I need to tell it which view I want to use. Yes. Now we see the Logan phantom. So yeah, by just specifying the full path to the viewer, we can then actually use it. Okay. Sometimes, especially if you want to work in environments where you can't really where you can't install all of these packages that I just installed, where you don't want to install FFTW or something like that. For example, if you want to use BART on an actual MRI scanner, might not be a good idea to install too many packages in that environment, or you might not get the right versions. So BART also supports static linking, which means just making a standalone executable of BART, which contains everything it needs to run on a Linux system at least. So in this BART directory, we actually created BART, and if we look at its dependencies, we see it uses quite a number of shared libraries at runtime. These are the ones we would expect. So it needs FFTW, it needs PNG, it needs LAPAC-E. But let's make a version of BART without this. For that, we first clean up. There is make all clean, which just basically puts our repository into a clean state again. And let's do static linking. With that, we again can modify our make file that we created earlier, and just give it at the option slink equals 1 for static link 1. And then we type make again. Again, we need to wait for quite some time because this is a slow machine or a virtual machine on my own computer. This only takes a few seconds. And now it again created a version of BART. And if we again ask for its shared library dependencies, it will just say, this is not a dynamic executable because it is a statically linked version of BART. So if I now copy this version, it would work also on other machines without, they don't have the dependencies installed. I think we can actually see, this is not human readable. If we look at at BART here, we can see it's now 36 megabytes of a 36 megabyte executable, which, yeah, that's the price you pay for including all dependencies in that version. Okay, and I think lastly, I want to show debugging. So how do you do debugging with BART? Yep, good, I have GDB. Yeah, we would recommend to use GDB. And with GDB, we can, for example, say, okay, we want to debug the phantom command, for example. So we do --args, give it the executable we want to run, and the command we want to run. For example, we want to create a phantom of size 128 in kspace, and we want to create it in the parent directory and call it fan. Then GDB starts. And from here, we need to tell it, okay, where do we actually want it to stop? Because if I now just say run, it will do it, and it will say, oh yeah, that process exited normally, because it's just something that works in BART. So if we want to stop at a specific point, we actually need to read, okay, where do we want it to stop? So we look at the source code for that, for the phantom command, which is just in source phantom.c. And I would just stop right at the end. Okay, let's not look at the source code here because I need line numbers. Somehow I thought it would give me line numbers, but it doesn't. Yeah, let's navigate here to source and to phantom.c. Okay, and I just want to, for example, stop in line number 201. Then I can go back to GBB, restart it, and say break phantom.c line 201, and then tell it to run. And then it will actually run and stop at this point. And now I can look at the environment. But what's actually quite nice, what I can do, if I have the source code here, I can actually also call functions from here. So if I just call, for example, we have a debug print dims function. Print dims function, which prints dimensions as it suggests. For example, we need to give it some dp info, so it actually outputs something. Then we tell it, okay, please print the dims, which is this variable here in line 199, and it will tell us, okay, this is an array of 128 by 128. Or we can also output a CFL file from this debugger just by saying C for call, dump CFL, then the output file name, which is just called debug fan. Again, the number of dimensions and the pointer variable over here. And if we then look, if this created something, we see here we have this debug fan CFL. Which is
in K-space.
Empty.
Empty.
Yeah, it's empty. That surprises me.
Maybe you stopped after the unmap.
Oh yeah, I stopped after the unmapped. Yes, I stopped here in 201. If I had stopped at 199, it would have worked. Okay, but in principle, you can also dump CFL files from this. And with that, I think I am finished. And yeah, I would give it back to John if there are no more questions for me to answer.
Okay, well, thanks so much, Christian. So I think the main takeaway from this is that to compile it on your own machine, there are a number of instructions you can follow, and then there are certain operations that are worth doing. For example, running tests to make sure that the build environment was successful, adding viewers so that you can view things without other dependencies, and then debug tools that let you actually inspect the source code as you run it. Now, all of this does require some understanding of build environments, especially with Linux, and so there is a little bit of a learning curve, but hopefully this does help get you started, and in the future, if there is interest, we can provide more information on that. But once you have a build environment set up, now you can start modifying the C code itself. And there are different things you may want to do, for example, adding simple things like parameter options or full-fledged tools. Before we do that,